So basically, as you can see, this is your section 2.1 handout that you can find in D2L. So now we're getting into, how to evaluate these functions, how to simplify the functions, talk about, like I was saying, addition, subtraction, multiplication, division, kind of how to do all of those operations. And we will also talk about how to solve these functions. So this little chart over here is probably something you want to keep in handy. I think you should be able to probably, save this image or something on your desktop, or, you can get it out of your textbook also. But these are all the different identities. Of course, we have the reciprocal identities, the quotient identities for your tangent, cotangent function. Remember, we had also talked about how we have these Pythagorean identities in chapter 1 also. So we're actually bringing them over here. We had looked at the co-function and also the even and odd, basically if your function was even or odd, what kind of behavior they would do. So all of these can play a part in, when you're trying to simplify these functions or solve your equations or any of these different examples we'll be looking at. So keep this handy because this will really come in use, when you're working through this. So the first part we're actually going to do is evaluate our functions over here. So let's start with the example that I have, number 8. This is coming from section 2.1. Okay, so this is what we are looking at. So they're basically saying use the given conditions to find the value of all 6 of our trigonometric functions. So looking at number 8, they're telling us cosecant of x is -7/6, and your tangent function, tangent of x is also positive. So let's see what that does, when we're trying to evaluate these functions here. So let's go ahead and write this down. We have cosecant of x equals -7/6. And they're also telling us that your tangent function is going to be positive. So if you think about this, in which quadrant is our tangent function going to be positive? So this would be quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So where do you think your tangent function is positive? In which quadrant? Abdul Aziz, very nice. Because remember, since we define our tangent function as sine over cosine, so basically the idea is if our tangent function is going to be positive, that means your sine and cosine should have the same, positive sign or negative sign. So either both of them should be positive, or, both of them have to be negative. So that happens in quadrant 1 because here, both our ordered pairs will have positive values. So your sine and cosine will both be positive. Or in quadrant 3, where both your sine and cosine functions are negative. So, now we need to see, okay, out of quadrant 1 and quadrant 3, where are the rest of our functions going to fall? So how can you move forward when we know that the cosecant function is -7/6? What other functions information can we get from the cosecant function? And this is probably where, you want to look at these different identities. So cosecant can help us come up with which other function value. Very nice. Yeah, because cosecant is the reciprocal function for sine function, right? And you can see that. I'm not sure if this is too tiny to see, but you can see how we define the cosecant function as 1 over sine function. So you can use that relationship to come up with your sine value. So let's see how we can do that over here. So if cosecant is defined as 1 over sine function, what will you do to find the value of sine function from this cosecant equals -7/6? And you've actually done similar examples like this in chapter 1. So how will we find the sine function here, guys? Because remember, conversely, we can also define the sine function as 1 over cosecant.
So do we just kind of like switch the cosecant and the sine?
Yeah, basically, yeah, very good. So does that help you come up with the sine function? Shu, what do you think your sine function will come out to be? Because if you're setting up sine of x as 1 divided by cosecant of x, and your cosecant function is given to you as -7/6, Scotty, very nice. You are taking -7/6 and you're putting it in the denominator underneath 1, and then, simplify that, which will come out to be, and Scotty, I guess you only sent me that answer, will come out to be -6/7. Remember, and I have talked about this multiple times now, you can basically invert that fraction from sine to cosecant or cosecant to sine, and literally just by inverting that fraction, you get the reciprocal function. So sine of x is going to come out to be -6/7. And this basically tells us that if your sine function is a negative number, then you are actually looking at quadrant 3 for all these function values. So we know our tangent function is positive. That means both sine and cosine actually have to be negative values, because you're coming up with your sine function as -6/7. Does that make sense, guys? So there's a whole process, right, involved in trying to figure out which quadrant your function falls into, and then using the given information to try and come up with, the remaining functions that you have over here. So how do you think we can find since we know the sine function, we can probably calculate our cosine function next. And that's again where you want to fall back onto these properties, these identities over here. So since we know what our sine function looks like now, you can actually use this Pythagorean identity over here to help you calculate the cosine function. Since you already know the cosecant function, you can use this identity to calculate the cotangent function. So there's multiple different paths you can take. You can go directly to cosecant and cotangent. From cotangent, you can get the tangent function. Or, if you find sine and cosine, then you can do the sine function divided by cosine function, to help you find the tangent function. So many different ways that you can use these identities to help you, come up with the other values. So let's do our cosine function next. So since we are using the identity sine squared plus cosine squared equals 1, this Pythagorean identity over here, oh, stop doing that. Okay, so what we are trying to do here is we're going to try and rearrange this formula a little bit, because we're trying to solve for the cosine function. So the first thing we are going to do is go ahead and subtract our sine function and move it to the right-hand side. So basically, we are getting the cosine function by itself. And this is again basic algebra skills that you are using over here. So we'll do 1 minus sine square of x. But since you still have that square on the cosine function, remember we end up taking square roots in this case, which will give us, one positive and one negative root. So your square root and square cancel out, leaving us behind with just cosine of x equals positive or negative square root of 1 minus sine square. But then remember what I just said, because our sine function is negative, but our tangent function is positive, then we know both our sine and cosine functions need to be negative. So actually in this little formula that we just came up with, we don't need that positive answer. So we are actually going to discard the positive answer and just keep the negative answer from this one. So this is what we're going to use over here now to find our cosine function. So we're going to have cosine function equals negative square root of 1 minus the sine square function. Are you guys okay so far? So basically we are just rewriting that Pythagorean identity and solving it for our cosine function over here, and then just keeping the negative answer because we know our cosine function has to be negative. So now just go ahead and plug in your sine function on the right hand side, and this will give us 1 minus, and then your sine function is negative 6/7, but then we have to square that. So we get square root of 1 minus, and of course you are doing negative 6 to the over 7 to the second power. So negative times negative will become positive, and then when you take a square, what do we end up getting on this? For negative 6/7 squared, what does that answer end up looking like?
36/49.
Very good. Yeah. So you're just taking 6 times 6, which is 36. 7 times 7 is 49. And negative times negative becomes positive. So you're doing 1 minus 36/49. And at this point, you can use a calculator to simplify this, but please keep in mind, we do not want decimal answers over here. We still want to keep them as fractions, and if you have a radical or whatever it ends up coming out to be. So just to show you, if you were trying to do 1 minus 36/49, we would basically need to find a common denominator. So we would multiply the 1/1 by 49, which would end up giving us 49 minus 36 with that common denominator of 49. And this will end up giving us what, 13/49 when we clean that up. And then, just go ahead and simplify. Very nice, Scotty. So yeah, we have, just coming back to our problem over here, negative on the outside, square root. Now on the inside, we have simplified this as 13/49. So remember, with square roots over fractions, you can break it up as square root of 13 on the top, square root of 49 on the bottom. So, of course, that will end up giving us negative. Square root of 13 cannot be simplified, so leave it as it is. Square root of 49 will, of course, end up becoming 7. And as long as that radical is not on the denominator, we are good to go. So this guy is going to be your cosine of x. And you can see we need to keep that negative sign on our cosine function.
So if,
Yeah, go ahead.
sorry. If you knew the cosine and you were trying to find sine, would you be able to use that identity too, and
Yeah.
just get the sine alone?
Yeah,
Okay.
very good. Yeah, so in that case, you would then try to get, the sine function on the left-hand side and move the cosine to the right-hand side.
That makes sense. Thank you.
Okay, yeah, you're welcome. So I was just saying that this is just one way of doing it. Remember, I was telling you it will depend on, which identity you choose to work with. And then based on that, you may have a little bit of a different approach. But as long as your calculations are correct, you should be able to come up with the same function values. All right, so at this point, we have sine and cosine functions both. So we can now use the quotient identity to help us find the tangent function. So let's do that one next. So tangent of x is going to be sine of x divided by cosine of x. So remember, our sine of x is -6/7. And then we're dividing that by the cosine function that we just found, -√13/7. So, again, use your little algebra skills here. So the function on the numerator or the fraction on the numerator stays the same. Then we change division to multiplication and invert the bottom fraction. So this guy will now become 7/√13. And, of course, it has a negative sign. So negative times negative will, of course, become positive. And we know our tangent function has to be positive. Your sevens will cancel out. And this will leave us behind with, let's see, +6 on the top, +√13 on the bottom. Now, WebAssign is one of those funky programs which will let you type this in for the most part, but I know some problems they want you to rationalize the denominator, which is what we normally do. So to rationalize, just multiply both numerator and denominator by √13. So this guy will end up becoming 6 times √13/13. So just see what WebAssign does, but technically we should rationalize our denominator. So, this is the answer that is preferred. This is only for WebAssign. All right, so let's see, we've got sine, cosine, tangent, and of course, cosecant was given to us. So we have 4 functions now. Since you also know your cosine function, we can actually find its reciprocal function, which is, the secant function. So remember, secant of x can be defined as 1/cosine of x, or vice versa, we can define cosine of x as 1/secant of x. So what do you think your secant function's value is going to be now? Don't send your answer just yet. I want to give all of you a chance to try and come up with that answer. So when I ask you, send the answer through chat, but don't do it just yet. And honestly, since now we know the tangent function also, you should be able to calculate the cotangent function as well. So go ahead and send me both of those. Just put a comma and separate your answers. So the first one, give me what your secant is. And then for the second answer, tell me what the tangent function should be. Cotangent, sorry. And of course, cotangent also is a reciprocal function for the tangent function. Okay, so if you're ready, go ahead, send your answers. Alrighty, let's see. I am getting for, again, the first one should be your secant answer, and the second one should be the cotangent. So I am getting negative 7 square root of 13 over 13. I've got positive 7 square root of 13 over 13, but looks like you've given me negative 7 square root of 13 over 13. And for cotangent, you guys are sending in square root of 13 divided by 6. I've got negative square root of 13 over 7 from you. Square root of 13 over 6, square root of 13 over 6. Okay, so that's the answer for the cotangent. And then looks like negative 7 square root of 13 over 13 for the secant. All right, so let's take a look at that. Our cosine function. Okay, Billy. All right, got it. Yeah, so basically, remember what I said, you can just invert your fraction to find your reciprocal function. So since cosine is negative 13, negative square root of 13 over 7, when you're finding the secant function, you invert that. So the negative will stay, but then you have 7 over square root of 13. But, again, we want to rationalize that denominator. So very nice, guys. Yeah, you should have negative 7 square root of 13 over 13. So very nice. And then, of course, for WebAssign, if they're silly, they let you type this in, but I'm not a fan of this answer. Okay, good job, guys. And then, of course, same thing with the cotangent function. So for this one, I would actually go to the non-rationalized answer because that will be easier to work with. So if you use for the tangent function 6 over square root of 13 and you invert that, that will end up giving you square root of 13 over 6. So, it's already taken care of because your square root is on the numerator and we don't have to worry about rationalizing this denominator. So just invert that fraction. Now, another thing you should notice, since your tangent function was positive, your cotangent function will also be a positive answer. And then since cosine and sine were negative, cosecant and secant are also going to be negative. So, it kind of helps you keep track of those signs. So cosecant was already given to us, so we didn't have to find that answer, but basically you had to find the remaining 5 of them. So question on this example, guys. You have actually done something similar to this in section 1.3 or 1.4, one of those earlier sections where we had done something similar where you had to figure out what quadrant your angle is going to fall into. And then based on that, we would know what signs our function is going to have. All righty, so that was number 8. Now the next one we're actually getting into is talking about this idea of simplifying. Let's make this guy a little bit smaller. So here we're actually talking about how we can simplify our expression. So again, this is kind of, that same thing of bringing algebra into trigonometry. So you can see we are talking about doing some factoring, maybe using one of these identities to help us simplify our example. So we are looking at number 22 over here. So they're saying use the fundamental identities to simplify the expression, and we are looking at number 22 over here. And as you can see, they are telling us there is more than one correct form for each answer. So, it will really depend on you individually, which fundamental identities you end up using and how you are kind of thinking about breaking this down. So, just keep working with these examples and you'll start feeling more comfortable with them. So let's go ahead and write this guy down. There we go. So this one is number 22. And let's see, we are given sine square of x multiplied with secant square of x, and then we are subtracting sine square of x. So, since they're asking us to simplify this, the first thing I would start with is, that negative is basically separating the two terms of your function over here. So you want to see what's common on the left-hand side term with the right-hand side term. So basically on either side of the negative sign, what do you think as something being common between those two terms over here?
Sine squared x minus sine squared x.
Yeah, sine squared, very nice. So sine squared is what you're going to see is common between both sides. So we're actually going to go ahead and factor the sine squared of x outside. So you're taking the sine square from that first term outside. So it only leaves you behind with this secant squared. So secant squared of x, you're keeping that minus sign. Now, since we're taking the sine square outside, there's nothing left over here. So remember, when there's nothing left, you put 1. It's kind of that same idea, if you had, and I'm just using, numbers over here to kind of show you, if you had, let's say, 3x squared minus, I don't know, x squared over here. So, x squared would be common between both our terms. So we would take that x squared outside, which, of course, this guy can be simplified in other ways. But basically, the idea is if you take the x squared outside, you're left with 3 from the first. But then since this x squared is gone, you put a placeholder, which would be the 1. So that's kind of the same idea over here that we're trying to apply. Now, what can we do with the secant squared x minus 1? So this is where you want to try and bring in some of these fundamental identities. So we've got secant squared of x minus 1. So which identity do you think we might be able to use, for our advantage over here? Okay, let's see. I've got Abdulaziz sine squared times tangent squared. So you're actually giving me the answer over here, but you are actually looking at this middle Pythagorean identity, because think about what happens if we rewrite this identity. So you have got, and I'm going to do this on the side here. So we have 1 plus tangent squared of x equals secant squared of x, right? So this is the identity that I'm using over here. So if I want to get my tangent squared of x by itself, all I have to do is subtract this 1 on both sides. So that will end up giving me secant squared of x minus 1. So you can see we can rewrite this. And now I have secant squared of x minus 1, which I can actually rewrite as tangent squared of x. And, of course, we still have that sine square of x from the top over there. Can we simplify this further? Or is this how far we go? Now, in this case, it actually wouldn't help, but, of course, we know, and we'll do this again on the side as some scratch work. So you've got sine squared of x, and you've got tangent squared of x. But remember, tangent, again, can be written as a ratio of sine over cosine. So technically, I can actually rewrite my tangent squared of x as sine squared of x over cosine squared of x. And I still have my sine squared from here. But this does not help me because, if my sine square functions were on the opposite sides, we could have canceled them out. But since your sine square are technically on the same side, we cannot cancel this out anymore. So we cannot really go any further than that. So this will actually be your simplified answer. So you are taking sine squared multiplied by tangent squared. And right now, in our trigonometry class, it will not make much sense of, why do we need to rewrite these functions? Why do we need to simplify them? The application for these actually comes into a calculus course, because that is where we will see, depending on what information we have, how we can manipulate it. A lot of times you have to simplify these functions to help you come up with, answers that you are looking for. So if you guys do plan on taking a calculus course after this, then you will actually see how these simplifications and these different fundamental identities come into play. So for our class purposes, this is more about just manipulations, just trying to see how we can modify these functions, how we can simplify them. So that's kind of what you are doing in this example, is just, cleaning it up a little bit. And you can see there are going to be, oh, go ahead.
So will WebAssign accept either answer or just specifically the sine squared x times tan squared x?
So they don't want you to really leave a lot of fractions in your answers. So you definitely don't want to go what I was showing you here in the green. We don't want to try and, leave them as fractions. So that's the reason why we're stopping at sine squared x, tangent squared x. But yes, WebAssign does have multiple different answers that it will accept, just as long as you are, simplifying it as far as you are able to take it.
Okay, thank you.
Yeah, you're welcome. So I just wanted to say that you do have a couple more different examples in your handout over here. There's, example 2. And then if you look at the video lecture and the notes, you will see I've also talked about how to simplify this problem number 2 over here. So, take a look at some couple different examples to get an idea of how the simplification works. And we'll be doing, a few more examples as we move forward. Now, the other part we're getting into is what we've already talked about a little bit, is just factoring. How can you use the concept of factoring in also helping us simplify these trigonometric expressions? So for this one, let's take a look at but number 26 over here. So this one is asking us to basically factor, use the fundamental identities, and as you can see, they're again telling us there can be multiple different correct forms of our answer over here. So we're looking at number 26, which is secant secant of x to the 4th power minus tangent of x to the 4th power. So let's take a look at what this guy will do. Okay, so any concepts from algebra coming to mind that we can use in this example to try and factor this?
Pythagorean theorem.
Pythagorean theorem. Trying to think how that could work. Because, obviously there is this Pythagorean theorem here, which uses the secant and the tangent functions, the one in the middle that we just used. But I don't think we're quite ready to jump to this example just yet, because I think we're going to need a little bit of clarification. So in terms of algebra, just imagine if you had an expression, something like a to the 4th.
Can't you use property rules as far as like exponent rules?
Yeah, because you are going to need some of those techniques in here. And Abdul Aziz, I just saw you sent in a square minus b square plus a square, times a square plus b square. So what's happening over here is, guys, we're actually going to have to do a little bit of manipulation over here, because with the 4th power, what you can actually do is incorporate, if you remember difference of squares talks about, when you have a square minus b square, you can factor it into a plus b, a minus b. So we can use this concept of factoring from the difference of squares And what you're going to do is rewrite your a to the fourth power as a to the second power, and then put a 2 on the outside because we know 2 times 2 is 4. Same thing with the b to the second power, and put, the 2 on the outside. So now what's happening is this thing is acting as your a over here, and the b square is just acting as our b. So that's your a and b, and then you have your squares on the outside. So using this rule of a plus b, a minus b, you will end up breaking this down into what Abdul Aziz has in chat. So this will break down into a square minus b square. So that's going to be this a minus b factor, from our difference of squares. And then this guy, you can write it as a square plus b square, which will be the second factor over here. But now you will see your first parentheses is a square minus b square, which is this original form of our difference of squares. So you can actually break that first parentheses further down into a minus b and a plus b. But then the second factor of your a square plus b square will stay the same. So if factoring is something that you haven't done since your college algebra course, and it's still you're a little bit shaky on that, then remember your chapter P, I think in this textbook for your trig, goes over a lot of these techniques. So if you want to just review, go back to chapter P for your textbook and kind of look through some of these examples for that. So this is the idea that we need to bring in to our example over here. So how do you think this will translate between your secant and tangent function? How will we write it out? So take a minute and think about it, and let me see what kind of answer you are able to come up with. Abdul Aziz, you've got secant squared plus tangent squared of x. What you want to do is think about a as being your secant function, b being your tangent function. So here you've got secant minus tangent, secant plus tangent. Yeah, and that's kind of what I was hoping that we would be able to come up with. But actually, I'm realizing we may not have to go that far out. So how about instead of going, yeah, Abdulaziz, that's kind of what I was thinking about, that property, the Pythagorean property between tangent and secant. So instead of going all the way down to a plus b, a minus b, how about we go from here first? Because I think we'll be able to simplify it without going all the way through. So in this case, what if we break down our secant and tangent functions as secant square of x minus tangent square of x. So that's your a square minus b square. And then this guy will be secant square of x plus tangent square of x. So we're actually doing this step right over here. And the reason for that is because as I was looking at your Pythagorean identity, you can see here we have 1 plus tangent squared equals secant squared. So if we rewrite this guy, you can get 1 equals, if I move my tangent to the other side, this guy will become secant squared of u minus tangent squared of u, which is what we have in our example. So we will be able to actually replace that and say, oh, that is equal to 1. So that's kind of what I am looking for. So right over here, your secant squared of x minus tangent squared of x, this guy will become 1 from your Pythagorean identity. So you will basically have 1 times, secant squared of x plus tangent squared of x. And we cannot simplify that part. So that will be our simplified answer. So basically we are using the Pythagorean identity, 1 plus tangent squared of x is equal to secant squared of x. But then if we subtract that tangent and move it to the other side, we get 1 equals secant squared of x minus tangent squared of x. And that's the property we have used right over here. So like I said, each one of this is going to depend on what fundamental identity do we have, how far we need to break. Because as I was kind of looking through my example, I was like, okay, if we break it all the way to a plus b, a minus b, then we're not able to use any fundamental identity in that case. So it made more sense to stop at our a square minus b square and a square plus b square step. So just again, trial and error, try and see what you are able to break this down as. Do we need to go that far, or is it okay to take a step back and not break it down all the way? So question on this one. So you're basically using the difference of squares as your factoring property over here to try and break down this example in here. And then, of course, we fell back on our Pythagorean identity to get rid of one of those factors by using this little, substitution over here. So that was coming from how to factor these trigonometric expressions. And again, you will see you can have, something like these examples. This is kind of similar to what we just did, but then you can actually also have this trinomial format to your factoring also. So this is probably where you want to think about, your perfect square trinomials, where we have a square plus 2ab plus b square, and this guy factors into, the same factor, a plus b squared. You can also have a square minus 2ab plus b squared, which will factor into a minus b squared. Or remember just the factoring that we talked about again in college algebra, is where, you try to see, what factors would multiply to give us 6, but then add up to give us -7, which in this case, since you actually have a 2 over here, this should be 2 times 6 in that case. So, a lot of your perfect square trinomials kind of factoring, how to factor just any 3-term trinomial, and that's kind of one of the same things that's happening in this example here also. So look at your video lectures if you have not looked into it already. You can see how in this first example, we are looking at, with this 3-term, how this factors into, 2 binomial terms. So that's actually the next example we're getting ready to get into. And looks like that's number 32. So let's see how we can use some of this 3-term trinomial kind of factoring. Okay, so what do we have for 32? And the reason I picked this example 32, because you will see both our functions are different. You have sine square in the first term, but then you have cosine of x in the middle. But then look at number 30. Number 30 has both cosine functions, in the first term and the middle term. So number 30 is actually going to have a little bit of a different process of factoring that than you will with 32. So I wanted to show you 32 when you have 2 different functions on that. So how would we go about breaking this guy down? So let's take a look at how to factor this one. Let's go ahead and write it down. So we are given sine squared of x and then we have 3 times cosine of x plus 3. Now, for any factoring to work, we need to have all the same functions. So either this entire statement we need to rewrite in terms of the sine function, or we need to rewrite in terms of the cosine function. And since I'm looking at sine square as my leading term, that actually, again, going back to our fundamental identity, since we're talking about sine square, the Pythagorean identity comes to mind. So we can go ahead and look at this first one over here, which is sine square plus cosine square equals 1. So you can see how this guy has sine square. So we can actually rewrite this identity to help us solve the example we're looking at. So let's go ahead and bring this guy over here. So our Pythagorean identity is sine squared of x plus cosine squared of x equals 1. So how do you think we can rewrite this to help us simplify the sine square function over here? What would you rewrite this Pythagorean identity as? Yeah, so Abdulaziz, you're moving your cosine to the other side of the equation. So you want to try and isolate the sine square, because again, we can make that substitution happen over here. So let's go ahead and subtract our cosine square and move it to the right-hand side. So these guys will cancel out here, and leaving us behind with sine squared, sine square of x. Okay, come on, there we go, is equal to 1 minus cosine square of x. So if we use this as our substitution over here, and I'm going to put this in parentheses for now just to show you that this is what we substitute in. So I will replace my sine square with 1 minus cosine square of x and leave the other terms as it is, right? So now you will see I have actually rewritten this entire expression in terms of the cosine function now. So we've got 1 minus cosine square of x plus 3 times cosine of x plus 3. Since you have positive 1 and positive 3, we can go ahead and combine these guys together. So that will actually leave us behind with negative cosine squared of x plus 3 times cosine of x, and 3 plus 1 will give us 4 over here. So now we have converted it where we are now able to, take it a step further and factor it. So that's actually the difference between like that number 30 and 32 that I was telling you about. When you have two different functions, you have to find a way by using these identities to rewrite the entire expression in just one function. So either it should have been all in sine or in cosine, and doing cosine is the way we needed to go with this example, because we would not be able to put it in the sine function format. So cosine was the way to go. Now, when you're factoring this, remember when we are factoring even in algebra, if you are given negative x squared plus, and I'm just using, these same numbers as an example, it's really hard to factor if you have a negative on your leading term on the x squared. So normally, if you remember in algebra, we'll always factor out that negative sign. It's kind of like you're bringing a negative 1 outside. So when we bring a negative outside, your x squared becomes positive, the 3x will become negative, and your 4 will become negative. But then it's easier to factor, when your x squared is a positive number. So we're going to apply that same technique over here, and we are going to factor out this negative sign, bring it outside. So that will make your cosine square a positive term. The middle term will become negative. So this becomes negative 3 cosine of x, and this guy will become negative 4. And now we're going to try and factor our parentheses. So now think about this. This is just like we do any 3-term, trinomial in algebra. What will be the factors where two numbers multiply to give us negative 4, but when we add, they add up to negative 3? So what do you think those numbers need to be? Now with 4, you're not going to have too many options, right? It's either 1 times 4 or 2 times 2. And then, you're of course playing around with our signs. Do I put the negative on the 1 or do I put the negative on the 4? And, with -2 and 2, it really doesn't matter where you put the negative since it's the same number. So Abdul Aziz, you've got -4 and +1 as your factors here. So when I multiply -4 with 1, my product is -4. But when I add -4 and +1, I get a -3. So yeah, very nice. We are then able to factor, this guy into, I guess we'll do it over here. We can factor this. That negative will stay on the outside, from here. This negative stays on the outside, but then we factor our parentheses into x minus 4 and x plus 1. So that's the same technique we are going to be using with our trigonometric functions here. So the negative will stay outside. Okay, and then this guy will break down into cosine of x minus 4 for the first parentheses, and then cosine of x plus 1. So literally just using the same expression here, but instead of x, we're using cosine of x. So take a minute, look at this, and see what questions are popping up in your mind. So just as a recap, we started out by taking our sine square of x function. Using the Pythagorean identity, we rewrite the sine square as 1 minus cosine square of x. Use that to substitute in our expression over here because we want the entire function to be in terms of cosine, because that's the only thing we can do. We cannot convert this back into a sine, so we convert it into cosine. We combine the 1 and the 3 to give us +4. Since you have a negative on the cosine square of x function, we pull out or basically factor out a negative sign. So that changes all the signs inside the parentheses, positive cosine square of x minus 3 cosine of x and -4. And then we're basically factoring what we have in the parentheses, and that factors into cosine of x minus 4 times cosine of x plus 1, and then this negative sign will carry forward. So this is what our factored form is going to look like for number 32. So just a different way of, how to use factoring. So remember, you've got these two types of examples here from example number 3, but then in example number 4, it's a little bit of a different factoring because you can see we're actually using two different functions over here, and you're trying to convert it into one single function. So my tip to you guys is look at what the middle term is, the single term, not the square term. Whatever is the single term in the middle, that's actually what your final function will end up having. So like here in this number 4, since my middle function is tangent of x, your final answer will also be tangent of x, something, and tangent of x, something. So it's always the middle term, which actually lets you know what the final functions will be in your expression. So that's a really good guide to kind of take a look at. So we're still continuing with this concept of, how to simplify our trigonometric expressions over here. So just another form of that same example we did in, number, I think it was example number 1. So we can take a look at, how to simplify that. And then we're actually getting into what happens if you try to add these trigonometric expressions. So let's take a look at our next example here. Let's see, that would be number 38. Okay, so this one is just again saying same thing, use your fundamental identities to try and simplify. And number 38 over here is cotangent of u, sine of u, plus tangent of u, cosine of u. So this one again is going to be a little bit of a different approach when we're trying to simplify this. Let's go ahead and write this guy down. So 38 is cotangent of u, sine of u, plus tangent of u, and cosine of u. And again, we're trying to simplify this. So we're trying to see how we can, break this down. So between the cotangent function and the sine function, on the left-hand side of the plus sign, do you see any way we can simplify those to, instead of having, cotangent multiplied by sine, if we can try and combine them somehow? So what do you think is the relationship between cotangent and the sine function? And, again, if it helps, take a look at these identities over here. So how can we break that cotangent and sine function down? Yeah, so for the cotangent function, very nice, Abdul Aziz, you can actually use this relationship over here because we define cotangent as cosine over sine, because it's the reciprocal of the tangent function, right? So we can actually use that to help us even break down just each individual side. So we'll begin on the left-hand side. I can rewrite that cotangent as cosine of u over sine of u, and then of course we're multiplying this with the sine function. If it helps, you can write that guy as over 1. So this is coming from cotangent of u being defined as cosine of u over sine of u. So you will see sine on the bottom, sine on the top. They will end up canceling each other out, which leaves us behind with cosine of u over 1, which of course is just the cosine of u function. So kind of using the same idea, what can you do on the right-hand side over here? So again, what identity can you use on the right-hand side to try and simplify it?
Would you use tan u equals sine u over cosine u?
Yeah, pretty much. Yeah, very nice. And Katie, I just saw your answer also. So yeah, very good. So you're kind of doing the same thing you did with the cotangent function, but this time we're using it with the tangent function. So we can rewrite our tangent as sine over cosine. So when we translate that over here, this will become sine of u divided by cosine of u, and then multiplying it with the cosine of u function. So same thing, the cosine on the top and bottom cancel each other out, and we are left with just sine of u. And so you end up with cosine of u plus sine of u. Can we break it down any further than this, or this is how far we go? Because if you had sine squared, cosine squared, then you could have used the Pythagorean identity, right? But since we don't have the squares on these functions, we don't really have that option of using the Pythagorean identity. So I think this is as far as we can go in simplifying this. So this will be our final answer. So you can kind of see, your instructions were the same, use fundamental identity to simplify, but you can see how each function has to be treated differently just based on, what is given to you. So that's why I kind of keep saying, we have to use a little bit of trial and error when we're working through this. So let's take a look at number 48 here next. And this one is actually talking about how we can perform addition or subtraction with these trigonometric expressions. So number 48 is this one over here. We're given cosine of, sorry, cosine of x, not that one. Cosine of x over 1 plus sine of x, and they're asking us to add this with 1 plus sine of x divided by cosine of x. So, how do we use these trigonometric identities again to help us simplify something like this? So let's take a look at this example over here. So again, guys, we are still falling back on our skills that we learned in algebra. So anytime you are adding two fractions, with different denominators, we have to find a common denominator. And, I think I actually just copied this from your textbooks. It's a little grainy, but the idea is, you would take this fraction and this fraction and try to find what your common denominator would be, and then you try to simplify it. So when we use that in our example here, if this denominator is cosine of x, and we will need to multiply it with the denominator on the left. So we multiply this fraction by 1 plus sine of x. And then on the left-hand side, we would multiply this fraction by the denominator on the right. So that would be cosine of x. So you're basically multiplying, with each other's denominator to try and find that common denominator. So on the numerator, you are multiplying cosine of x with cosine of x. So that would actually just become cosine squared of x. On the denominator, we are basically taking 1 plus sine of x and multiplying it with cosine of x. I'm actually going to leave it as it is. I'm not going to distribute it. And then on the right-hand side fraction, we are taking 1 plus sine of x and multiplying it with itself. So I'm just going to put the square on the outside for now. And then our denominator will be again 1 plus sine of x being multiplied with cosine of x. So now you will see our denominators are the same, but of course we got to clear out our numerators. So just kind of looking at this, what do you think you want to do next? How would you proceed from this stage going forward? Do we want to go ahead and FOIL that 1 plus sine of x with the square on the outside?
No, you should,
Sorry, Scotty, go ahead.
no, I'm a step ahead. Never mind.
Okay, so I think, Jack, I saw you shaking your head into a yes, and then Abdulaziz, you're also saying yes. So that's where I would start, because there's really not much we can do. You've already got cosine of squared of x on the left-hand side numerator. So yeah, let's go ahead and FOIL our right-hand side numerator over here. So let's see what that would end up looking like. So I'm going to do this over here. We've got 1 plus sine of x, and we're multiplying it into itself, 1 plus sine of x. So 1 times 1, we're just following our FOIL step. So 1 times 1 will give us 1. So that's this step over here. Then you do 1 times sine of x plus, then we do sine of x times 1, which again will be the same thing here, plus sine times sine, which will, of course, end up giving us sine squared of x. Then combine your two middle terms. So sine plus sine, it's kind of like, x plus x, which gives you 2x. So that would be the same thing here. This would be 2 sine of x. And then, of course, we've got our sine squared at the end. So FOIL that. Now what I'm actually going to do is, instead of leaving this as two separate fractions, since we do have the same denominator now, we can go ahead and combine these into a single fraction. So we've got cosine of squared of x from the left-hand side, plus I'm going to put this simplified, the FOILed answer over here. So that will be 1 plus 2 times sine of x plus sine squared of x. Okay, so we took the left-hand side, brought it down as it is. The right-hand side, we did a FOIL on the 1 plus sine of x, and we have the FOILed answer. Now think about this. What fundamental identity can I use to simplify this further? Abdulaziz, you're talking about changing cosine square into 1 minus sine squared. What else can we use instead of rewriting cosine into a sine? Yeah, actually, look at your fundamental Pythagorean identity over here. They're telling you sine square plus cosine square is equal to 1. And don't we have sine square plus cosine square over here? Because you are adding cosine square with sine square over here, right? So if you want, you can go ahead and bring these guys next to each other. You can have sine square of x being added with cosine square of x plus the 1 plus the 2 sine of x, because this is addition. You can rearrange the order of your terms, and then we know sine square plus cosine square is going to be equal to 1 from this Pythagorean identity, and that will actually help you simplify this. That's fine, Lowell. Yeah, we're just wrapping up this example over here, so that should be okay. So as you will see, we can combine those guys together, and I'll put my denominators in later. The sine square plus cosine square will become 1. And then you are left behind with 1 plus 2 of sine of x, right? Now go ahead and add the 1 plus 1, which will give us 2. So you'll end up with 2 plus 2 sine of x. What can we do after that? After you go ahead and combine this, what can we do next? And I'm just putting in my denominators over here. Okay, so what do you guys have? Yeah, very nice. And again, guys, as always, I only get answers from Abdul Aziz. I know you guys are also, I need you to participate. So I know if you are understanding this or, you're having trouble understanding this. So please try and plug in some answers, push something through. So once you go ahead and rewrite that sine square of x plus cosine square of x as 1, you add the 1 plus 1, you will see on your numerator, you have a 2 in your single term over here, but then we also have a 2 with that sine of x. So you can actually go ahead and factor this 2 out. So if you bring this 2 outside, from that first term, we put 1 as our placeholder, plus from the 2 times sine of x. If you're bringing this 2 outside, then we are only left behind with sine of x. And then look at your denominator. What can we do?
So then you're just left with 2 over cosine x?
Yeah, go ahead and cancel out that parentheses part, because 1 plus sine of x on the top will cancel out with 1 plus sine of x on the bottom. So, after all of that, you can see we are able to simplify this actually into a very small term, because you will end up with 2 on the numerator and cosine of x on the denominator. Remember, we defined cosine 1 over cosine of x as the reciprocal for the secant function. So this will actually become 2 times secant of x. Yeah, very nice, Abdul Aziz and Alicia. So yeah, rewrite that 1 over cosine as your secant function. Remember what I was telling Scotty a little bit earlier when we were discussing that normally we don't want to leave fractions when we're simplifying this. So don't leave it as 2 divided by cosine of x. Rewrite that cosine, for the 1 over cosine as secant function. So this one is a little bit more involved because you have to find your common denominator. After you find your common denominator, you have to see how you can simplify your numerator. Once you simplify your numerator, then you can see it actually starts cleaning up pretty quickly. So this might take a little bit of time to get used to, but again, work through your examples. Let me know if you have any questions. So any questions stand out right now as you are looking at this example here? Okay, so as I was telling you, your 2.1 homework and quiz are open. I will try opening the remaining chapter 2 sections also. And then as I'm done with class, I will go ahead and reopen the chapter 1 homework and quizzes if you want to try and get some higher grade on those. So have a wonderful spring break, guys. If you want to stay back and ask me questions, you can. If not, I will see you on March 22nd. Don't get into trouble. Stay safe, everyone. Be careful. Bye, guys. Take care.
Thank you.
Thank you. Bye-bye.